All right, so who here knows about reason? Well, it's, wow, okay, oh, cool. Quite a bit of people. Are you guys excited? I'm pretty excited. Here's a little bit of disappointment, though. I'm not here to talk about reason today. I'm here to talk about imperfection. The background picture is Japanese philosophy called wabi-sabi. What wabi-sabi basically celebrates is this beauty in imperfection and in ephemerality in life and blah, 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 you know. Philosophies, right? So, it's kind of nice. It ties back to what I'm going to talk about today, which is imperfection and trade-offs. But first of all, a quick intro about myself. My name is Cheng Lou. I work on Reason at Facebook. Reason is a new syntax for OCaml, a language we already use at Facebook, with a nice sound type system, great performance, great interop with JavaScript. Again, I'm not here today to talk about Reason, though I'll use Reason as a case study in a few examples to illustrate the broader point, software engineering point I'm going to make today. So again, trade-offs. As a thought experiment, think of a recent software project or library, or the last one you just saw in JavaScript, if you want, and think how good the documentations are, how clean the repository is, what are the performance guarantees, and feature-wise, does it promise to solve all your problem, or does it promise to solve, like, what kind of subset of problem does it actually solve? What's the trade-off, basically, right? The truth is, in reality, most of our software are trade-offs. We don't have infinite time, we don't have infinite energy, and as software engineer and not computer scientists, as software engineers, that's us, engineers, making decision against a limited budget, limited time, limited complexity, limited learnability, etc. And making trade-off in that sense is almost like an art. You can't cram everything into your software, nor do you want to do that. And just because you have infinite time doesn't mean you should blow up your project to whichever size it could be. But more important than that, a trade-off isn't just, like I said, it's not just an artifact of unfinished work, right? Some trade-offs are very tasteful and very intentional, and this is the topic I want to explore today. And first of all, I like to have a more formal term for describing trade-offs in the context of this talk, and I'll call this 80%. Right. Whenever I say 80% as opposed to 100% in this talk, I mean some trade-offs were made, either accidental or intentional. And as in, for example, this API covers 80% of your needs. Right. If you don't like it, maybe wire it up with some boilerplate and use it, or maybe use a completely different library, right? 80% in terms of coverage and in terms of this correctness relative to this idealistic 100% that we're trying to aim for. And to be clear, 80% doesn't actually represent the numerical 80%. It could be 60%, it could be 90%. The general theme is that it's imperfect. So far, so good? And the opposite of 80% is 100%, where you assert some universal quality. In math, for example, there's the concept for all x something something, right? Or when I say this algorithm is guaranteed to terminate, it's a for all property here. Or this type system is 100% sound and doesn't bail on you. These are the examples. And for me, the interesting part today is that I'm going to pit 80% against 100% and see the trade-off of both approaches. And to do that, I'll be focusing on the 80% aspect. For me, it's a much more interesting problem to realize how we can make tasteful trade-offs and what are the heuristics of doing so, rather than talking about 100%. 100%, conceptually, it's easy to think about. It's just you do everything in your domain, right? It's hard to do, it's hard to achieve, but it's not hard to understand. 80%, it's much harder to understand. And I want to start with the advantages of when you try to make these kind of tasteful trade-offs, what you get as a software artifact in the end of this 80% methodology. And the very first thing I want to talk about is something called the Pareto Principle. The Pareto Principle is the hallmark of this 80% approach. It basically says that in real life, if you look at this graph, when you invest 20% of the effort, you sometimes get 80% of the result, right? It's not a linear progression where you invest 10%, you get 10% back, and it's more like this curve. Hello. Thanks. By the way, a movie I want to plug today is Inside Out. You might wonder why I want to plug this movie. I plug a movie every talk. And Inside Out is a great movie because it also shows you that all aspects of life is needed, including sadness, when they don't, spoiler alert, I guess. When joy doesn't realize that sadness also plays an integral part into the well-being of someone, and when joy wants to overly optimize for this 100% happiness, and doesn't realize that trade-offs is actually part of a healthy human being. There you go. Sponsored by Pixar. Okay, now back on topic. The Pareto principle is basically a more formalized way of saying, it's a good bang for the buck, right? It's a good investment. And under a more popular term, this is called the sweet spot. That's what we're talking about when we talk about sweet spot. It's a nice local maximum. It's not necessarily the most scalable solution, but for what you put, the energy you put in, it's pretty good as a result. There's a deeper explanation again of why, statistically speaking, why this curve actually happens. But instead of explaining that, I like to point you to some successful use cases of the Pareto principle in software. The first one everybody knows is image and video compression. Okay, more specifically, lossy image and video compression. So at the bottom, if you can see clearly, you have this strip, 5 pictures. The leftmost one is the original one without any modification. It's 100% preserved, no compression. And the rightmost one, if you zoom in, you can see that there's a lot of fuzziness to it, lots of picture compression artifacts. And on the top, what you get is basically mapping this picture into this frequency domain and then optionally clipping it. Frequency domain mask, we call it. And basically the concept is, there's this high concentration of data in a certain region, and we're going to take that and disregard the other pieces of data. And as long as we capture this conceptual 80%, at the end, it's worth it because you get a picture that is almost as good as the original one, but it's only, say, 1/10 of the original size. And this is a nice trade-off in lots of cases. For example, mobile, in which case you can see 9 more images, which kind of makes this approach more worthy. And since this is a React conf, React is a very, very good example of 80% executed well. I hope you recall the first time you tried React in the playground or something, you write this tree format, and we even have a dedicated syntax for this declarative tree. You render it, you hook some state up, you render it again, it does a performance diffing for a tree diffing algorithm, etc. And everything was nice, right? Until one day you use it in production, and all of you inevitably stumble upon this awkward period of learning React where you want to do some sibling communications, right? You have a deeply nested node, and then you have an uncle node, and then how do I communicate between them? And then all the turns come from there. And then it dawns upon you that this tree model maybe wasn't ideal, right? It wasn't the final abstraction. Because in reality, user interface programming, it's a graph, right? It's not a tree. The generalized model is a graph. Why is it a graph? Well, look, pop-ups, it's a graph, right? Transcends these kind of tree layouts, layouts constraints, sibling communication, right? Cross-view animation, that's not a tree at all, that's a graph. And the realization is that maybe this is it. Maybe this is a sweet spot we will stay at. And you know what, this is okay, because for 80%, or more realistically, 95% of the time, it is actually a tree. so React paradigm optimizes for that, and for this real life realization where we say, it's okay if 5% of the time it's dirty, if we sacrifice this, developer experience to optimize for that 95% of developer experience, it's a worthy trade-off. And here's another example, unidirectional data flow, right? It takes real engineering maturity in this regard to understand that as much as we like to admit that in real life data actually flows in two directions, most of the time in our UI application, unidirectional data flow is actually good enough. And the entire React paradigm actually optimizes around that. It's real engineering taste and maturity, I would say. And the lesson you can learn from this is that some things are really not meant to be optimized. Remember Inside Out? You don't want to optimize something away and then realize that there's a part of the software engineering that you've been missing or stuff like that, to be hand-wavy about this. And React's stance is basically, let's not try to do everything. Let's not try to cover 100% of the use cases. Some part might be unsolved for a long time, but you know what? We'll escape hatches and life moves on. And in the JavaScript community, more general, in the programming community in general, it's sometimes a little bit too easy for people to criticize these approaches. It's always easier to criticize, right? And they don't see that when something's 80% done, sometimes it might be intentionally 80%, not just accidental, not just because some developers on the core React team ran out of time or anything like that. It's because this is the sweet spot, and it's nice to be there, right? And oftentimes, I also hear people say, you know, this isn't ideal, let's fix it. And as much as I can applaud this effort, you gotta understand that sometimes there's also a sense of dread when I hear that, because if you go back to this graph, by criticizing or ironically by contributing more to an intentionally 80% project, you actually pulled it out of its sweet spot. And now it's not hitting any sweet spot, it's just caught between this awkward diminishing return phase where you contribute more to it, and then the more you contribute to it, the less return you seem to get, right, in terms of velocity. And of course, contributions are always welcome, and this is just an extreme argument to make you realize that this situation indeed exists in real life. Feature bloat, ironically, is caused by contribution from folks who don't necessarily grasp this sweet spot, but want to still contribute to the project, right? Now, the second thing that this kind of 80% trade-off approach enables is creativity and simplicity. And it's a great advantage because some properties, mathematically speaking, naturally speaking, are simply lost when you try to generalize and abstract over everything, when you try to have this unifying ideal abstraction over all programming paradigm or whatever you want, you lose occasions to optimize things, both in terms of developer experience and performance and tooling opportunities and all. And the prime example in this category is DSLs, right? Domain-specific languages, some of which we use every day. Regular expressions, great DSL. Infix math notation. Syntax, right? Syntax is not generalized at all. It's just like optimized for these few constructs we use every day and few data structures. The JSON syntax is an extremely great example of that. GraphQL, SQL, etc. And it's not possible. You have to realize it's not possible to have the terseness of regular expression and the performance of regular expression if you try to make it cover all the string operations, right? Just like when you put a tree algorithm into a graph and you want to solve that graph algorithm, it becomes NP-complete very quickly. It's not possible to do it in 100% methodology. And the third point I want to illustrate with this is that the 80% approach is actually a very adaptable approach. It's a very flexible approach. There was a saying somewhere that says the people who survive in society and all, they might not necessarily be the strongest people, they might not necessarily be the weakest people, they're the most flexible people. They can just survive through everything. And this is what the 80% approach gives you. It's that, you know, pre-allocated empty wiggle room. That's what I would call it. It's that unknown wiggle space. If you do things 100% correctly and you plan everything in advance, You don't have this wiggle room. Everything is by definition already planned, already determined, right? And by giving this wiggle room, for example, for the Unix tool, the Unix pipes and stuff like that, you give room for this potential organic growth. Everybody says the Unix tool doesn't scale and everything, like it's text-based, it doesn't parse correctly, it doesn't have a communication format, yet the Unix tool move on and it stays around, right? And this is the inherent reason why it stays around, this extra wiggle room. All right, so we send enough praise for the 80% approach, so let's look a little bit at the disadvantages just to be fair. And first of all, it's pretty obvious. A badly done 80% is extremely brittle. Right? It's an 80% approach. It's not very great for foundation building, right? Things that don't need any, that don't have very good room for innovation or anything. Like standard library, like just make a good one, just make 100% good one, and then freaking move on with their life or something, right? Don't bike shed around it too often. There's like it's not innovative to have a crazy standard library or anything. Type system kind of belong to this category too. Well, it's math, and you kind of wanted to guarantee certain property, etc. Language semantic, also in this category, maybe more or less. You can debate on some of these points, but the general idea is there. And JavaScript's designs, kind of as an example, efficiently employ this 80% Pareto principle. It employed it very well. The author of JavaScript designed it in a week. Pretty darn good for a week's work, right? Come on, a week's work, right? Everybody's using it now. But then due to unfortunate historical circumstances, we pulled JS, the scripting language, out of its comfort zone, out of its sweet spot, and now we're using this 80% sweet spot language as a 100% language. And no wonder all the patches and patches and patches and all these problems that keep arising. It wasn't designed for that at all. And fortunately, we've patched this up through the year so that now it's actually a pretty neat language to work with, to be honest, albeit that took a lot of effort. But still, some of the developer experience and performance optimization are unfortunately forever out of our reach because of this non-solid foundation. But you know what? That's life. The second thing is this 80% approach of making trade-offs it makes composition very hard, right? Once you have a mutation in your chain, very hard to work with. Side effect in your chain of composition, suddenly your operations are time dependent. When you work in the 80% paradigm, one bad apple really spoils the barrel, right? Also, I'd like you to realize that this is not a plug for Reason or anything like that. Reason also has mutations opt-in. It also has side effects. It's in the Reason's case, it's actually an intentional design decision for pragmatic reasons and performance. But since we're on the topic of Reason, I do want to single out one topic, which is the 100% types of Reason. Lots of languages who have type system tackled on, they have this 80% type system where you cover it 20% and then you get 80% of the benefit, which is great. But Reason types don't bail, right? They don't bail on you ever. People come into the Discord room and they say, "Is this sound?" I'm like, "It's Reason code. It is sound." And here's an actual anecdote. During the conversion of Messenger.com at Facebook to Reason. And I've played with Flow and TypeScript before too, so you see that once you convert this one file over, and then convert a second one over, and third one over, you get this funny feeling that you are actually creating islands of pristine 100% code. This is a realization that I've never heard anyone speak of in the gradual typing and pure typing community, so I want to raise this today. There are two ways of doing gradual typings. Gradual typing doesn't mean you take 10 files and type all of them 20% correctly, right? Gradual typing can mean you take 10 files and you type 3 of them, for example, 100% well. This is also gradual typing in terms of quantity, right? And because we give you this kind of soundness guarantee, these 3 files will never go stale. These three files, when you work with them, you get this monotonically increasing benefit. It's like a constant payoff. Whereas with the gradual typing approach, and again, I'm not making any emotional judgment here, I'm just employing the Pareto Principle. With the gradual typing approach, the first 20% gives you 80% of the benefit, and then you realize it's a diminishing return afterward. It's much harder to actually get to 100% this way. And you still worry about whether that bug is in one of these files in the untyped region. Whereas in the reason code, you don't worry about it. You know in a very black and white way whether it's in one file or another. So here's my actual plug for reason, honestly. I urge you to try 100% type system or 100% system or 100% whatever paradigm library or anything. It feels day and night in terms of difference. Right? It's not the same at all. It's not a gradual progression. Once you hit that 100%, it suddenly goes like this. Just think about the last 100% paradigm you've worked with. Think about math, for example. It just magically composes and you don't know why. All right, so of course, as a side note, still as a plug for reason, this part, 100% type system is also harder to adopt. An 80% one is easy, so by contrast, a 100% one is hard, which is why we, in Reasonland, we've attacked the problem of the adoption through an unrelated angle, which is making the interop great. So, and this way we overcome the difficulty of adopting a 100% type system by making the interop very simple. So these two kind of cancel out each other, and in general, the adoption story has been really great, despite this 100% sound type system. And also thanks to the fact that our stance on mutation on side effect is 80%, right? It's more flexible this way, so interop with JavaScript is relatively easy, just as a side note. So what's the lesson here? It's all about trade-offs, 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 and more trade-offs. But hopefully by now, you see that there are benefits to consider either of these two approaches, right? Software is actually a blend of judgments. You don't do 80% all the way or 100% all the way, right? It's, you do what's right for the situation. Use the right tool, etc. And something to think about next time you try a language or a library, right? Is it 80%? Is it 100%? What is it trying to do? What's the scope? How do I contribute effectively to this library without killing it? And here's another insight. 80 and 100% are complementary. I myself love a well-crafted 80% library, as you can see. I like React. I've worked a little bit on React too. I don't mind if doing some things in React is a bit harder, if it means that 80% of the time is smooth sailing. Can everybody agree with that? I don't mind set state isn't 100%, because 80% of the time it does hit a sweet spot. It's easy to add, it's easy to remove, there's no ceremony needed. I kind of like it, honestly. But as much as I love 80% well-crafted library, you need a bit of 100% in your system in order to do what I call growing your sloppiness budget. Sloppiness as in 80%. It's a real luxury, folks, to be able to use an 80% approach with 20% of the energy. You don't get to do that if your foundation is also leaky, right? Your foundation has to be good. Your foundation has to approach 100% for you to have the luxury of using sloppier methods, right? And you don't get much wiggle room otherwise if your standard library or language semantic is kind of broken between different implementations. So as a very real anecdote, the other day I had to code mod messenger.com through some reason React changes, the new API which will come out very soon. And basically, frankly, in the OCaml community, we don't do these kind of 100% refactor too much. What I used to do for this change in particular is I used sed, right? Sed, the Unix tool that changes string, potentially in a file, in batches of files. Sed is this 80% tool, right? Extremely easy to use for these kind of 80% situation when you can. So what I did was I grabbed through a few words, changed them, the spacing changed, the length changed, and then I passed them through reformat, all of them. Reformat is a 100% tool. So the syntax is now pretty well formatted. And then I pass them through the compiler, which is 100% and doesn't bail on you. So the compiler catches the last wave of error I would have made using that 80% tool. Right? This enables me to use this 80% tool. You'd be crazy to use set on a large untyped JavaScript code base. Good luck trying that, okay? Tell me what happens. Speaking from actual experience, I tried that and it wasn't pretty. So as a case study, small case study for a reason of 80% and 100% and the relationship between them. Reasons type system, again, 100%. Language semantic, 100%. One implementation. Documentation, 80%. This is not a tasteful trade-off or whatever. This is just bad. Like, it should be 100% documentation. But you gotta understand that historically speaking, OCaml, like JavaScript, also has some kind of words. And OCaml used to be a primarily research-focused language that happens to be pragmatic for real-life use cases. And so the documentation was a little bit lacking, and this is what part of the Reason project is trying to improve. Documentation and low-hanging fruit kind of polish. Tooling 80%, I'm kind of ambivalent on this one because it's nice to be able to stay in your terminal and use ls and cat and pipe things into one thing into another, and then just keep things lightweight and simple. Use familiar tools. But on the other hand, I would also like to have a really great refactoring tool and all of that, and a really great 100% graphical user interface to accompany that. So. This is a little bit of a personal taste thing. But objectively, it is 80% for the majority of OCaml. BSB, which is the buckle script build system, for the JavaScript build system. Probably the most tasteful 80% project I've seen in the last few years. BSB is extremely performant. It doesn't take care of bundling. It doesn't take care of all kind of like asset loading or whatever. But for what it does, I urge you to try the JavaScript workflow on the Reason page right now and just start BSB and change one file and tell me how many milliseconds it took for it to compile again. Right? It's probably the fastest build system compiler in the mainstream language besides Go or some others. Promotion. By promotion, I mean all these kind of meta things like Stack Overflow support, blog posts, evangelization, and all. The OCaml community does 80%. When they have a good idea, they talk about it, but otherwise they stay kind of silent, kind of like in an academic manner. I would like this to be a little bit closer to 100%, but I understand that they don't want too much this kind of fuss, this kind of extra language thing. So, personal opinion still. All right. So also, sorry, you can do the same exercise for JavaScript to see what is 180. So here's a small conclusion. No, actually, here's a big conclusion. As a side note, okay, Leslie Lamport, the godfather of distributed systems, once wrote an article that I urge you to read. This is somewhat related to what I talk about today. He argued that as software complexity grows, we kind of more and more tend toward using this kind of 80% fuzzy biological approach. And he doesn't say that in a very nice way. And I want to give you an example of this. In math, when you write down a theorem and everything, right, you say, well, for all situations like this, and assuming you satisfy axiom 1, 2, 3, then here's the result. In math, if you write a paper and you say, well, 80% of the time this kind of works in my sample size of numbers, nobody takes you seriously, right? But people take you a little bit more seriously if you do that kind of things in physics, right? And they take you a little bit more seriously when you do that kind of things in chemistry, a little bit more seriously when you do that in biology. They take you seriously if you do that 80% approach in psychology and then sociology, right? Why? Because sociology is complicated. Too many factors into play. If you want to model it 100%, you can. It just takes 1 million variables. You can fine-tune them. It's just very hard and tedious. So they think the Pareto Principle and this kind of constraint is a nice sweet spot because for 20% of the variable amount, in this case more like 5, 6 variable, you can get 80% of the result and you say, well, this experiment is probably likely a success, right? And I urge you to think about this kind of 80%, 100%. In the JavaScript community, we unfortunately got the short end of the stick. Most of the things we do are 80% kind of. But in computer science, you still have the chance to touch these 100% and enjoy the benefit of 80% and use more 80% approach, given a good foundation. Thank you.